recording. Okay, so welcome Year 9. This is going to be a bit of a review week based on your Google form submissions. So I sent out that feedback form and some of you responded, so I'm going to go through that. The idea is you can rewatch this webinar and other webinars this week. Go through your previous work this week to make sure you've completed it and submitted it, because I'm aware some of you have struggled a little bit. And then responding to teacher feedback. So anything that's been marked, your big questions, your Google forms, respond as needed, and then resubmit it so we know you've done that and we can check what you've put and make sure give achievement points, all that sort of thing. And then I've made a little mini review form based on all the others. So they're not new questions, they're questions you've seen before. So how many groups are there in the periodic table, because we've gone through that. And then because I know you're getting a bit fed up with staring at computer screens, I've make revision cards. You can make a nice poster. You can make a post-it note mat. So that's where you put all the key words down on like post-its and move them around if you like, that sort of thing. I quite enjoy doing that one. Or you could make recordings of your voice of the key bits. Some people like making voice notes and things like that. Obviously, if you want to do any of that, do feel free to share it with us. We'd love to submit some of that to the newsletter, because I'm sure posters and revision cards will look awesome, and I know what you guys are like for putting hard work into that sort of thing. So that's the plan this week. At some point you may get invited to a meeting with your teacher to go through some specific bits and have a chat, so a bit like a Zoom clinic but your teacher themselves. So my plan will probably be to do that with my class on the Thursday, as I'm in school on Wednesday, which makes it tricky for me to do it then. So I'll post a link for my class on the Thursday. As I said, it was a May, it depends on your teacher on that one. Okay, so is there any questions or any points people wanted to raise before I crack on?
Just one thing I'll point out is we are having our regular drop-in session at work slot 1, Wednesday, 2:10 to 2:55. At any point during that, you can come and ask specific questions. There'll be teachers available. So come and find us if you need help with anything we're going to go over today.
Yep, there you go. Okay, awesome. So yep, you've got your Zoom clinic, and you may also get invited in another science slot to have a little meet with your teacher. Okay. So as I said, this is a bit of a review based on the Google feedback, and this is why I've changed this slightly. So there's going to be a few explanations. Now I haven't put polls in this week, because you'll notice at the end I've put Kahoot. So I put Kahoot. I spelled it wrong. But I wanted to make sure we had time to go and play that. So that's why I've not put any polls in. However, do feel free to answer any questions that come up into the chat box. And I'm sure Mr. Collins will interrupt and shout them at me. I can see Q&A box going. Is there anything there that I need, sir?
Just people asking what we're going to be learning about, but I'm sure we're going to get onto that any second.
Okay. It's a bit of a mishmash, because I've taken topics that you guys have asked for to go over again. So I just wanted to sort of recap a few things. So for example, here we've got the first one was isotopes, and just wanted to recap what an isotope is. And can anyone in the Q&A box tell me which one of those is not the isotope?
A lot of them have spotted a cat, miss.
Yes, there is a cat. I couldn't find one with an isotope link, so I've just put in a charge link. But yes, there is a cat. There's quite a few cats. So which one of those pictures, if you want to go, I don't know, hang on, A, B, C, which one is going to be the normal one that you would see on the periodic table? So we've got A, we've got B, we've got C. Anyone answering, sir?
Yeah, we've got a few answers. I think a lot of people are saying the one with 7, they're identifying that. Some people are saying that is the isotope. Some people are saying that isn't the isotope.
Okay, and this is why we wanted to go through it, sir, so thank you. So the one that you would see on the periodic table is the middle one. And you should know, or hopefully this is recap, it's got 3 protons, which positively charged, which matches up with electrons. So we know there are 3 electrons, negatively charged. And then the top number, which is the mass number, is the number of protons and neutrons. So 7 minus 3 equals 4. So there are 4 neutrons, and we've got these lovely pictures which show that as well. And that is the standard one we see on the periodic table, meaning the other 2 are isotopes. Now, isotopes just change the neutron number. So you can see in the pictures, they've all got 3 protons, they've all got 3 electrons, but they have a different number of neutrons. That is the key thing when you're talking about an isotope. It just has a different number of neutrons. Okay, any questions on that before I move on off this bit? So isotope, different number of neutrons. And again, periodic table is always going to be your key when looking at these.
I've got nothing coming up in the Q&A yet, Miss. I think it might be good to move on.
Okay, awesome, thank you. So one other thing that came up was percentage abundance, and I've chucked in a few of my slides on this, okay? Now, you may have noticed that we call it relative atomic mass, and this links in with percentage abundance and isotopes. So there are actually 2 types of carbon, okay? The most common carbon that we have is carbon-12, and that's the one that we see on the periodic table. And again, you'll notice a question, so I'm going to see if people are answering that one. How many neutrons does carbon-12 have? Have we got answers, sir?
They're starting to come in.
Awesome.
And everyone that I'm seeing is getting it right.
Awesome. So 6 neutrons and then 6 protons. Excellent. Well done. Okay, now a tiny fraction of the carbon on Earth is actually an isotope, which is carbon-14. How many neutrons does carbon-14 have? Again, answer in Q&A box, and so can tell me how you're doing.
Just waiting for a few more to come in before I say how they're doing.
Okay, sir, that's fine.
And then we have got a question I'll bring up to you. But again, everyone that's submitted an answer so far has got it right.
Awesome. And just to double check, what's the atomic number of this carbon? I can see Q&A box going, sir.
Oh, okay. This one is less well answered.
Oh. Okay, so what makes an atom the atom it is the thing. Not the neutrons. Has that helped at all, sir?
Just giving them a little bit of time to catch up.
So what is the atomic number? What makes the atom it is? If I click back to lithiums, they are all lithium. What do they all have in common that makes them lithium? Okay, so there's something about all 3 of them. They're all isotopes, but they're all lithium. What's the same? I'm going to bounce back to that question. So what is the atomic number of carbon?
So a lot of people initially gave the mass number of 14. So
Okay.
Top is the mass number, not the atomic number.
Right, so yes, the top number is your mass number. Okay, so that's the mass of the atom in that nucleus, and then the atomic number has got to be, if it's not the top number, it's going to have to be the bottom number. So for carbon, it's going to be 6. Okay, and that's the number of protons. Does anyone need me to go over that again? So this is the mass number, the big number is the mass. And then the bottom number is the proton number, the atomic number. And there's a lovely key on your periodic table that actually tells you this information when you have a periodic table. So always remember that.
But lots of people have got the right answer now of putting in 6. Well done to those people. Okay. Natty's got a question. Do isotopes lose or gain neutrons? How do they get different amounts of neutrons?
How do they? I think, well, most commonly they're just there unless they're a radioactive one. Am I on the right lines, Mr. Collins?
Yeah, that's exactly what I'd say. So let's take chlorine as a really good example. Chlorine has 2 stable isotopes. So there just happens to be 2 configurations of chlorine that the chlorine atom is stable enough to persist for a long time. And some of them have a mass of 35 and some of them have a mass of 37. And it's just random when the atoms are created inside a star during fusion, forcing elements together to make larger elements. Sometimes they have a few more neutrons and sometimes they have a few less. The ones that are unstable, that don't have a stable configurations of protons and neutrons, they're radioactive and they will decay and change, but you will learn more about that when we do some physics.
And I thought I'd change my slide to match up with you there, sir.
Wonderful.
So on the slide, we've got the 2 isotopes of chlorine. So most common one is 35, and then a quarter of the chlorine of the other ones I mentioned, which is 37. And that's why you tend to see on periodic tables that chlorine's relative atomic mass is actually 35.5. Okay, and that's often a common question, but why is there 35.5 on chlorine? Well, it's because it's a relative atomic mass of chlorine based on the different isotopes.
Yeah, it's kind of an average.
Yeah. Any questions on this before I bounce?
None have appeared just yet, miss.
Okay, awesome. I'm going to bounce. Okay, so one of the things you have to be able to do is calculate relative atomic mass due to percentage abundance. And percentage abundance is just the amount of it there is. So as we just said, there's chlorine and there's 2 of them and there's a different amount of each one. That's the percentage of it around. Okay, now one of the ones that you can look at is on the board here. This is boron, and it's got 2 isotopes. It's got isotope 10, which is 20% of the boron that's around, and then boron 11, which is 80%. And then you might get asked, what is the relative atomic mass of boron from these numbers? So what you would have to do is multiply the mass number, so the top numbers, by its percentage abundance. So boron 10 by the percentage of it that exists, which is 20, and then boron 11 by the mass of it which exists, which is 80. And then that would give you 880 for both of them, for that one. Then you add them together, which gives you a grand total of 1080. Divide it by 100, and then that would give you the relative atomic mass of 10.8. And if you were to round that up, it would round up to 11, and it would match the periodic table. And one of the key things I actually say with these questions is check what the periodic table is telling you the relative atomic mass is, because if your number's way too far from that, then you've probably made a little mistake or missed a number somewhere. Okay, and that's actually a key point on some of your calculations. I know for my class, check your numbers, because some of you on the lovely bond energy calculations are set 2 weeks ago, you had lovely working out, everything was right, but you'd switched a 2 for a 3 or a 3 for a 4, and it meant you dropped all your marks. So always double check your maths. Is there any questions on this slide? Okay, this was based off the feedback form, by the way, guys. That's why it's in here.
Yes, you absolutely get a periodic table in your exam, only in the chemistry exams, though, not in the physics or the biology exam.
Which is why I keep referring to it, because it's really, really, really important to use that periodic table. Okay, I'm going to click on. I would get you to calculate this. It's up to you guys if you want to. Does anyone want to have a go at calculating, or shall I leave this in here for you to do in your own time? We've got 2. We've got thallium 203, which has an abundance of 30%, and then thallium 205.
People are saying, own time, move on, please.
Okay, all right, I'll move on. Okay, and then there is the answer there if you want to have a go later. Okay, I am going to get you to have a go at these. So look at the nuclear symbols for the 4 elements, J, X, Z, and A. We've got J, X, Z, and A. How many of these atoms have 8 neutrons in their nucleus? And I'm going to get you to answer this because I want to double check you've got how to work out neutrons. Again, answer in Q&A box for Sir, and Sir can shout me when he's got answers coming in. So how many of these atoms have got 8 neutrons in their nucleus?
Yeah, we're starting to get some answers in, and most people are getting it correct.
Awesome.
Some of you are putting it anonymously, so I can't shout you out, but Kaya, well done, you got it correct. Alice, well done, you got it correct.
Awesome.
Lots of anonymous attendees are getting it correct. 1 or 2 haven't quite got their head around it. But most people have spotted the correct answer. Miss, would you like to tell us what it is?
From my maths, I've got the correct answer as 2, because 16 minus 8 would make 8, and then that would tell me X has got 8, and then Z, 15 minus 7 makes 8, so I would get the answer as 2 of them have got 8.
Can you tell me how many neutrons A would have then, Miss?
A?
Yeah.
14 minus 6. Hang on. My maths is appalling, sir. Oh, no, that one's got 8.
Yeah.
Yeah.
So 3 of them have got 8, which
Thank you, sir.
correct answer. It's X, Z, and A. So well done to all of those of you who got this right.
And Mrs. being dozy. And which 2 of them are isotopes? Which 2 letters? So which of the 2 are the same element, but they're isotopes of each other? We got anything coming in on that one? Which 2 are isotopes?
People are starting to put some. We've got a few right answers.
Thank you for correcting me there, sir.
That's not a problem. Okay. Okay, so it's kind of more of a mixed bag, this one. I'd say about half the people have got the right answer. And some people have chosen, for example, J and A.
I can see why.
Answer. Yeah, I can see why too.
Okay, so J and A isn't correct because, yes, they've got the same relative atomic mass, but the thing that's changed in them is the relative atomic mass. So the answer you want is J and Z, because they both have the same atomic number, the same number of protons, and that means they're both going to be the same element. Okay, so if you think back to carbon, it would be carbon 6, and then carbon 14, carbon 15. So it's the bottom number that stays the same in isotopes. The only thing that changes in an isotope is the number of neutrons. Okay, hopefully that's helped. Are there any questions on this before I move on to the next bit?
I'll just give people a second to put a question in if they want to.
No worries, sir.
But some people are saying, can we go over this next week too? Remember, guys, next week is half term. We would strongly encourage you to take a break from screens and do something that you enjoy. But there will snow potentially. But we will have opportunities for you to go back over this again after half term. And then hopefully when we're back in school, again, there'll be opportunities for those bits which maybe you haven't understood for you to make sure you can get your head around.
And there's also the clinic as well, if they wanted to pop there and ask to go through it again. Okay, going to move on. Now, this came up as a bit that you wanted to go over, graphene and graphite. So I thought I'd chuck this in for you. Now, graphite is an allotrope of the 2 carbons with diamond, and it's here. Okay, the bottom picture here, hopefully you can see my mouse moving. And you can see you've got your different little hexagonal shapes, and they're all nicely bonded in sheets. And then there is some weak bonding between these layers. Okay, and you should remember that each carbon here is bonded 3 times, and that means there is a spare electron that can move around, which I've put up here, and it's delocalized. That's your key term, and that's why graphite can conduct electricity. Now, graphene is simply one of these layers. Okay, and it's really, really, really useful for numerous different reasons. Okay, so graphene is light, so it's very lightweight. It's got a very strong structure. It's 0.142 nanometers, and it's a good thermal conductor and electrical conductor, which is why there are many uses of it. The key difference between the 2 is that graphite is layers and graphene is 1 layer. Okay, and hopefully that's going to clear that up a little bit for you of the difference between the 2. So graphite, multiple layers, graphene, 1 single layer. Okay, really useful in circuits. Sir?
Yeah.
I thought you were going to say something then.
No. Question, which one is in a pencil?
It's graphite, isn't it, sir?
It is, yeah. Graphite
Yeah,
is in the pencil. When you draw the pencil over the paper, those layers are actually rubbing off the graphite and being deposited on the paper. That's how graphite pencils work.
because the layers can break easily, which is why it's slippy slidey, which is a point that I hadn't mentioned, sir. So
only weak intermolecular forces between those layers.
Yeah. Okay. Any other questions before I move on to the next bit? Oh.
So on paper, is it graphene, says Zach. Maybe if you did an incredibly thin layer, but most of the time it's not just one layer that gets rubbed off on the paper. So it is chunks of graphite coming off in larger than 1 atom thick layers.
Any more?
Do they both have delocalized electrons?
Yes. Yes, they both do, and that's why graphene is really, really useful. So they're both, these sheets, they've got the carbons bonded 3 times, and they both have the delocalized electrons, which is why they can both conduct heat and electricity.
Natty's asking, does that mean I can't make a diamond pencil? Natty, if you've got enough carbon and the heat and the temperature to change the configuration of the carbons, you can take a pencil and turn it into a diamond, but you then won't be able to write anything with it. It will just be a pretty thing that you have made, but won't actually make any marks. We've also got, if you had really thin knife, could you make graphene? The best way to make graphene is basically sellotape. If you use sellotape onto a layer of graphite and then lift the sellotape off, you can remove very thin layers of it. And with not much more complex technology than that, someone who worked at the University of Sussex won a Nobel Prize for ways of making graphene easily from graphite. It's difficult to scale up to make it mass produced, which is why we're not seeing loads of graphene products on the market yet. But one day we will get there, and it will be a genuinely fantastic thing.
Okay.
Can we electrocute the school with our pencils? No, no, no. This is particularly why you should not put a pencil into a plug socket, though. If you're sitting in a science lab and you've got one of those plug sockets in front of you, really incredibly bad idea to put your pencil inside it. Please do not do that.
Okay, and then I've just put some slides in, which I'm not going to run through, just summarising graphite and graphene for you. Okay. They're just there for information. And then fullerenes, they are carbon structures like this one here on the board. Again, similar properties, so soft electrical insulators, insoluble in water, low boiling points, and this leads into their uses. Okay, which I will get onto. I've got a whole slide of uses. One bit that I think me and Mr. Collins will go over a bit more after half term is going to be nanotubes and nanoscience. Because we're sort of going over it quickly. But what I wanted to do essentially get you to is the fact that they're very, very small. Nano means very, very, very small. And you can see that we've got our human eye range here, our light microscope range here, and then electron microscope range here. And this is where you'd typically find your nano. And N means nano. So this is the size of nanotubes and all those little nanoscience bits that you can see. They're very, 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 very small. Not quite as small as an atom, but small enough. As small as the DNA in your cells. Okay, so I've just put that in to give you the measurements and the numbers, because I know you were asking about that. And then this is just your uses. And as you can see, there's a lot of applications for nanoscience. I'm not going to run through them all, but you've got treatments and medical uses. Drug delivery is a common one that comes up. Used in the environment to detect things and as sensors. Used a lot in electronics for computers, and also a lot in space, chemistry, various things. And I'll leave this, as I said, you get these slides so you can have a nosy and read up on it if you are interested. Okay, metals and alloys was another bit that came up that you guys wanted to go over, and I just thought I'd put some pictures in. Hopefully you're getting the reference of why I put the cat in. We've got metals at the top, and you can see they're all uniform in shape, which means they can slide over them each other, which means they're easy to manipulate and bend. The bottom picture is our alloy, and you can see they are different shapes, so it's distorted, which makes it harder than a metal, and those are the key things that you need to actually be saying. So different shapes of atoms makes it harder because it's distorted and it no longer slides. Are there any questions on any of this, sir?
Not yet, but a quick shout out to Leo, Archie, and Laurie, and as well as a few anonymous people who all spotted there was a cat on this slide.
I quite like the book the cat's reading, sir. That's why I picked it. Okay. I am going to wiggle on unless there's any questions on any of that.
Someone's asking, would it be possible to make a working metal pencil? Before they had graphite in them, they used to have lead. And that was bad because people would sometimes have to suck the pencil in order to get the lead to move freely over the paper. And that meant they were ingesting heavy metals, which can't be processed out of your body. So they would slowly build up, and lead poisoning is a bad thing. And it affects the way your brain works and can cause mental illness.
Mm-hmm. Any other points, sir? Sorry.
No questions about metals and alloys yet.
And then essentially here is some common uses of alloys. So alloys, two metals. These are some of them. So dental fillings, and then brass, which is hinges and plugs, and then soldering iron, which is lead and tin. Don't know why it's called soldering iron when it's lead and tin, but that is used to join metals together. So I've just put that in again for you to have some extra information.
Yeah, just a word, modern solder doesn't contain lead. So solder from like back in the 50s was a mixture of lead and tin. But again, lead is a pretty dangerous metal if it gets inside humans. So they've now made solder that is lead-free. So if you've used soldering irons like Freya has, then you have not been exposed to lead. Don't worry about it.
Oh, I should change the slide then, sir.
Well, it's historically true.
Okay, last little bit that I'm going to run over before we get to the Kahoot is the activation energy. Oops, sorry. And this is the two graphs, because I actually like to see them next to each other so that I can work it out, because my brain otherwise struggles. So on the left, we've got our exothermic reaction. And one of the things I just want to mention is what activation energy is. So that is the minimum amount of energy needed to start the reaction. And the way I always remember it is if you've got a bit of paper, so for example, I've got this paper here, it's not combusting, it's not on fire. But if I was to get a lighter or a match or something to set it on fire, that provides that minimum amount of energy to start that paper burning, okay, and start that chemical reaction of the paper with the oxygen. So the activation energy is the minimum amount of energy needed to start the reaction. Okay, and exothermic reactions are the ones that release energy into the surroundings, and you can recognize the graph that you would get because your reactants are high, you get your energy in, and then you get more energy released. Okay, so where the point is where the reactant started, the products are down here, energy has been released. Okay, and then the opposite way is your endothermic, and that needs energy to start. So the activation energy you can see here is larger, so it's absorbed energy from the surroundings and the products end up higher. And hopefully this slide has helped with the two reaction profiles, that's what these are called, and what activation energy is and the difference between the two. Okay, because essentially you need to be able to draw these two shapes. So exothermic, you'd have your reactions high, products low, and then little dotted line to your activation energy, and then endothermics the other way around, reactions at the bottom, products at the top, and then energy being taken in for the reaction to happen. Are there any questions on this bit?
None coming in yet, miss, but if there are any, then I will shout them out to you.
Okay, awesome. The last little bit, and I'm just looking at the time, I don't know if I've got time to go over it, sir. I can't remember how long we've got.
Yep, we definitely have time.
Was your bond energy calculations, okay? And I just wanted to make sure we were all good on that. So what I've got here, just to show you, is the bond energy calculation table. Okay, now you wouldn't get given this whole table table in an exam, because there's a lot of bonds on there, you would just get given the bonds you would need. And these numbers don't change, and you're not expected to remember them, you're given them, okay? And I know bond energy calculations is something some of you have got off the top of your head and you're great on, and some of you have wobbled a little bit on, okay? And the reason I like to spend a lot of time on it is because I tend to tell my classes the first thing you want to do is find the bond energy calculation in your chemistry paper, knock it out and get yourself 3 marks, because once you've got the knack of it, it's 3 easy marks. I'm going to stop sharing my screen and I'm going to camera switch. Okay. Oh, there's a Q&A. I don't know what that is, sir.
Don't worry, miss. You crack on.
Okay. Okay, so hopefully you can see. Oh, bear with me. I'm just camera wiggling. On the sheet in front of me, I have got a bond energy table and a little picture of an equation. I'm hoping you can all see that one. Okay, and it's asking me to calculate the bond energies in this picture. And I thought I'd print it so you can see how I work it through on paper. And I'm just going to talk through this calculation once, and then we can move on to the Kahoot. So the first thing I want to do is work on 2 sides. So I've got my left and I've got my right. Okay, and I'm just putting a line down so I don't muddle the 2. And then my left side, I need to work out how many of each type of bond I've got from the picture. And I'm going to start with my carbon-carbon, just because the ones in the middle tend to get missed. So I've got a carbon-carbon double bond. There's only one of them, because I can't see anymore. I'm going to cross it off on my picture so I know I've included it. I'm going to look at my table. The number there is 614, and that's that done. I'm then going to look at my carbon hydrogen, and I can see if I count them through 1, 2, 3, 4. Okay, so carbon hydrogen, I've got 4, and then the number on the table that I've been given is 413. So that's the number I would put there, and then I would put that in my calculator and work out what that number is. But I'm sure someone is doing that at home, and so will shout out the number so I don't have to faff with my phone. The next bond I've got is a BR-BR, and there's just one of those. So BR to BR, and then that number is 193. And then I just add all these numbers up together. Okay. So while I wait for shout outs.
Can anyone beat miss on the calculation?
I am just trying to find my calculator. I've got a new phone, so I don't know where
It could be easy to beat miss then.
I found my calculator. So 4 times 413 equals 1,652. I'm hoping you can all see that. Possibly not. I'm just going to...
Luke, yeah, double check your answer.
Right, 1,652 plus 614 plus 193 equals, I've got 2,459.
Okay, some people are getting other answers. So go have a look at what Miss has done. There are 4 lots. Yeah, 4 lots of the 413.
52.
1652.
193. No, I've definitely got that answer, sir.
Miss has got it right. I'm saying there's some other people who've got other numbers. Have a look at what Miss has done.
Because you know how it is.
Yeah, absolutely. Have a look at what Miss has done. So she's done the multiplication first, and then she's just added up those 3 numbers. Added 614, 1652, and 193 together.
I'll circle them.
Okay. So, Miss, how would you go about attacking the right-hand side?
Okay, so right-hand side, and I'm aware I'm going to struggle with paper, so I'm just... Oh, hello. I'm trying to find a blank bit of paper and make it visible. Hopefully you can see I'm going top corner. Okay, right-hand side. I am going to start again with my carbons, because again, as I said, people miss this bond. So carbon to carbon, there's just one. It's not a double bond, so carbon to carbon equals 348. And there's only one of them. Then I'm going to look at my carbon to hydrogens, and I've got 1 here, 2, 3, and 4. So same as last time, 4 times 413, and because I've already worked that out, I can write the same answer in there. So 1652. I'm aware I'm cutting off a bit on the screen. There we go.
That's perfect.
And then I can see here I've got carbon to bromine, and I've got 1, 2. Okay, so carbon to bromine equals 2 times, check my table, 276, which is going to equal, and again, I'm going on to my calculator.
Anyone beat Miss again?
So
Answers
2
in chat.
times 276 equals 552. And then I've got to add all three numbers together again. So 552, just because I've got that in there, plus 348 plus 1652 equals 2552. Okay. And at the moment, that would get you 2 marks. Okay.
Hold on, Leo. Leo was only just a smidge behind you, Miss. So good job, Leo.
Okay. And then you have to work out for the third mark the overall energy change. Okay, so I am going to go with the energy in minus the energy out. So 2459 minus 2552, which has given me minus 93. And typically they don't actually worry if you have a plus or a minus there. They look at the total number. So my answer that I've got is going to be there.
Yeah, got someone, an anonymous attendee, getting minus 93. Well done. That is correct.
Okay, and now hopefully that has helped with that last little bit of bond energy. And I thought I'd show you how you do it with the paper and what I do to avoid missing bonds and all those sort of things, because you would normally typically have paper. Okay.
So someone's saying they thought you should just take the small one away from the big one. Technically, you should do energy in minus energy out. And then if you get a negative answer, that tells you it's exothermic. Think back to those energy level diagrams. If the amount of energy in the chemicals has gone down by 93, where has that 93 bits of energy gone? They've been given out to the surroundings because they're no longer in the chemicals. If the amount of energy in the chemicals has gone up, where has that energy come from? It's been taken in from the surroundings. So the surroundings are going to get colder. That's going to be endothermic.
Okay. Any more questions on that before we Kahootsy?
Change in mass. So would you write the change in mass as negative if it was negative? So for a start, we're not, the mass is the same here. We've got the same number of atoms altogether. So there's no change in mass. What we're calculating is a change in energy. But yes, to get it correct, technically correct, you should have a negative energy change for this one. But the way the exams are marked, you won't lose marks if you don't include the negative. So to get it technically correct, yes, it should be negative 93, but 93 is sufficient to get the marks in the exams.
Okay, I'm going to switch it back to me. Haha, hello. And I'm going to share screen. Bear with me because I've got to play around with my screens. My brain is not working. I'm going to stop sharing. Hang on. Stop share. Bear with me. That's why.
Those of you who are waiting, I would phone or a tablet or an extra browser window at the ready. Because I'm going to be taking part in this as well. So see if you can beat me.
I did that in the year 11 one with Mr. Lamsar. And
Did you come top?
Rushed. Huh?
Did you come top?
No, because I overrushed 2 of the questions and got them wrong, and then went, no, I put the wrong thing in. Because, yeah.
That's not fair.
It's a vital lesson. Don't rush it, man.
Okay. Some people are saying, oh, that's not fair that I'm taking part. Well, be better than me. Easy. And also, yeah, Miss Wanstall, I might get some wrong. I might think I know it, not read the question.
I got them wrong. It was the mass of an electron. I put 0 rather than the 1/2000. And I can't remember the other one, but I rushed essentially and then went, no. And it put, I got 3rd position. I was actually quite impressed that one of the year 11s beat me. Right, give me a second. I'm going to disappear from screen. I feel like somebody is playing on PlayStation and it's taking my internet. Yeah, I know.
Okay, so we've got, let's look at Q&A. Why aren't there generated names? The way this has been set up, it hasn't generated names automatically. Sadly, I was looking forward to being a secret squirrel or whatever it was going to give me, but that's the way Mr. set up this Kahoot. You have to put in your own name.
Oh, sorry, sir, I didn't set it up.
That's fine.
Are they behaving?
They are. We've got the real Natty. Most people are just putting their name. Someone's put F.
Yeah, I'm not sure what he was playing, but he was like, I've been playing it the whole time.
We've got a Joker Skittles.
Yeah. Are we all in?
Oh, no, there's still a few people joining.
Oh, Kaya.
Well, apparently he's the Bez.
Yeah, not the best. I'm not sure about that Johnny name. Hi, Natty. Hi, Laurie, by the way. Hi, Martha. Hi, Freya.
I've been told to wait by
Hi,
someone.
Archie. Hi, James. Hello, everybody.
Oh, waiting. They're still waiting. That's fine. I am waiting. We are waiting. Do not worry. People who are telling me to wait. 37 people in the Kahoot, 57 people in the webinar. So 20 of you, either you've gone off to make a cup of tea or you just don't want to do Kahoot.
I know, man.
Oh, man. Someone's phone's out of charge.
Oh, sorry. Okay.
Yeah, it's true, Natty. If someone else has put their name as Natty, then if that person wins, then Natty's going to get the credit. Not a great idea.
Are you not? Is Natty not the real Natty then?
Don't know.
Okay, I'm going to count down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and we're going to start. Nearly out of time. Oh, sir.
I got it right. I'm just a little bit behind in time. I'm taking my time. I'm reading all the options before I choose my answer. I don't want to do a Miss Wanstall.
No, you don't want to do Miss Wanstall. We're going to end up calling that a Miss Wanstall now. I don't mind. People learn from my mistakes. Well done. Question
Rory,
3.
I'm coming for you, Rory. I'm just behind you.
Oh, I haven't actually gone over this one today. Let's see if they know their bonding, sir.
Ah, right. Yeah. I see why that's wrong. I was like, aren't there 2 right answers? And then I went, oh, no, I see why that's wrong.
Well done, everyone. Nice to see you do know your bonding. Hey, Archie. Mr. Collins, you're in 3rd.
I'm slowly creeping up.
Well done. Oh. speed picking up on these, sir, which is really good.
Yeah, I'm getting faster. Brrr.
Oh, I might skip at 10. I'm skipping. I'm mean. Question 6. No, I haven't actually mentioned this. There's a clue. We shall see. Yeah, that one's on me. Graphite, graphene, non-metals, and I hadn't actually mentioned that it's the first 2D material. So well done to the 17 of you who got that. And hopefully you learned something from that one. Oh, Mr. Collins has hit number 1. Who's going to knock him off?
I think onions were the most likely.
We shall see. My money's on Archie.
Had to think about that one.
Yeah, I think if I was in a rush, I would have hit the wrong one.
I think there's 2 correct ones.
Oh, yeah, there is.
Yeah. Well,
Yeah.
that's me. I'm the one blue person who went for a poor insulator.
But that would be correct, wouldn't it?
Yeah, I think so. I feel cheated.
Yeah, sorry, sir. Oh. Very quick on look, take on this one. Yeah, well done, guys. I'm going to cut this one off at 10 if I can. Yeah, very, very small. Oh, I might not have mentioned this. This is a key pointer, but it's not that they're tiny. And I'm only giving you that hint because I'm mean. And I haven't mentioned it. But Sir may have. Let's see.
I think I did in the webinar, but I didn't spend a long time talking about it.
Yep, you must have done so because they knew. Well done, guys. Now, I've mentioned this one today. And process of elimination.
The clue is in the name as well.
Yeah. And they got it, sir, because they're legends. Oh. I wonder how many people are going to put me.
Genuinely not sure. Yeah.
There you go. Scratch-proof glasses and self-cleaning windows. I know.
You're dancing away to the music there, miss, but I don't know about everybody else, but I can't hear it.
Oh. Well done, guys. Yeah, my computer's music's quite low. I could doobie-doobie it. I'm not sure we're going to need all 50 seconds on this one. I'm going to give it probably till 40. Otherwise, we'll be here forever going on. Oh. And go. Well done, guys. We've got a bit of a split. So the amount of energy needed for a chemical reaction to take place, kind of, because without it, the reaction won't start. But we refer to it as the minimum amount of energy particles must have before they can react with each other. So it's just a terminology thing there, guys. 3 more questions. Well done. A little bit off. Remember, absorbed will be endothermic and released, it will be exothermic. Oh, Mr. Collins, you're back at the top. Let's see, shall we?
Good. I think people have got their heads around that now.
Yay. Right, last question. This might be a bit of a mean one.
I know the answer, but I'm leaving it till late. I'm going to leave it to the last moment so that if anyone else gets it right ahead of me, they'll get more points.
That's Buffy, by the way. I actually put Buffy in a quiz. Wow. Well done, guys. You know me well. I must talk about my animals all the time. Oh. Well done. Well done, Rory. Who is it, sir?
Well,
Colin.
by 53 points out of 1,366 is very, very close.
That is very,
well,
very
Rory
close.
and Jago, and who was that? Who was Onion, and who was it? Dot that came in 4th.
Well done, guys. Well done. Okay, I'm going to hit stop share and bring it back to our lovely faces. I am also going to hit stop recording because I realised I recorded the Kahoot, but people can play along later. Okay, so